Okay, so welcome to this next video in which we are discussing neurotransmitter release. So far what we've seen is how we can dock these synaptic vesicles at the membrane of the synapse, basically, at the active zone of the synapse. Okay, so what we now want to understand is how an action potential propagating along the axon and making its way into the axon terminal is going to actually trigger these synaptic vesicles which are docked at the active zone to actually fuse with the plasma membrane and release their neurotransmitter contents here into the synaptic cleft. Okay, right, so we will turn over the page and we will start with a discussion of the action potential then. So, if this is the axon here, and here's the axon terminal here, okay, so here's the axon terminal. Right, what's going to happen is that the action potential is going to arrive at the axon terminal. So what that means is that, let's say, this portion of membrane here is undergoing an action potential. Now, in the action potential, what happens is that the electrical potential difference across the membrane depolarizes. So the intracellular compartment's electrical potential goes up, basically. And the reason for this is that sodium cations enter from the extracellular fluid into the intracellular fluid. So you have raise the level of sodium ions in the intracellular fluid under this piece of membrane, basically. Now, the way in which this is going to propagate further along, basically, into this axon terminal, the way that this is going to propagate into the axon terminal is that some of these sodium ions are going to just sort of diffuse over into this neighbouring portion of membrane here. Now, if we draw a graph showing the electrical potential difference across the cell membrane, then if on this axis we plot time, and on this axis we plot the electrical potential difference from the extracellular compartment to the intracellular compartment. So let me stress to you what this means. This means have a little man standing in the extracellular compartment measuring electrical potential. Okay? He then moves into the intracellular compartment and measures electrical potential again. So, if I draw this membrane, here's the extracellular compartment has some electrical potential, which I'll denote electrical potential in the extracellular compartment. And the intracellular compartment has some electrical potential, okay? The electrical potential difference, or the voltage, from the extracellular compartment to the intracellular compartment means if I move from the extracellular to the intracellular compartment, how much does the electrical potential change? I.e., it's the new electrical potential, which is the electrical potential on the inside, minus the old electrical potential. Okay, now usually the electrical potential of the intracellular compartment is lower than the electrical potential of the extracellular compartment. So when you move from extracellular to intracellular, you go down electrical potential and usually it's around 65, we'll say, millivolts. So usually you go down by 65 millivolts, and that's what the meaning of saying that the electrical potential difference is negative 65 millivolts. It means that if you go from the extracellular compartment to the intracellular compartment, your electrical potential will go down by 65 millivolts. Okay, right, so it's usually somewhere down here, negative 65 millivolts. Right, now, when some of this sodium diffuses in from this neighbouring portion of membrane that's undergoing an action potential, what that means is you're going to put positively charged sodium ions here. So let's draw some of these positively charged sodium ions. So we'll colour this positively charged sodium ion in green. So you're going to move this positively charged sodium ion into that intracellular compartment. Now, when you put positive charge somewhere, that raises the electrical potential there. So, the electrical potential of the intracellular compartment is going to go up. Okay? Right. So, if we now ask what's the electrical potential difference from the extracellular to the intracellular compartment, well, it won't have gone, when you move from extracellular to intracellular, you won't go down quite by 65 millivolts anymore, because this one's gone up a bit, so the amount by which you'll go down is going to be less. If you want to think of this in terms of this formula, you can imagine this one staying the same, and this one having gone up, basically. Okay, so what's going to happen is that the electrical potential difference across the membrane is going to depolarize. It's going to get less negative. So this is the depolarization due to that sodium, so I'll highlight it in green. Okay, now as more sodium comes in, this will continue on happening. Now if enough sodium comes in, what's going to happen is you're going to reach a certain point known as the threshold potential, which usually is negative 40 millivolts or somewhere around there. Now, what's the significance of the threshold potential? Well, basically, in the membrane of your cell, you have voltage-gated sodium channels. So let me say this is a voltage-gated sodium channel. So this is a voltage-gated sodium channel. Let me just label it up, give it its full title. It is a voltage, and I should write bigger so it's nice and visible, voltage-gated sodium channel. Okay, now basically, this is usually closed when the membrane electrical potential difference is negative 65 millivolts. However, if the electrical potential difference across the membrane depolarizes to threshold potential for that voltage-gated sodium channel, which is usually negative 40 millivolts, then what's going to happen is this voltage-gated sodium channel, which I'll colour in red. Okay, so in red here is the voltage-gated sodium channel. It's going to open, basically. So, at negative 40 millivolts, what's going to happen is these voltage-gated sodium channels are going to open, and they are going to allow sodium ions from the extracellular space to go in through them into the intracellular compartment. Now, why does this happen? Well, it's because sodium concentration on the extracellular compartment is very, very high. Let me denote this by putting lots of green dots here. Okay, so you have lots of very high density of sodium cations on the extracellular aspect, and you have a low density of sodium cations on the intracellular aspect. So the concentration gradient is going to favour the movement of sodium in, simply because the chance that a sodium ion will hit the channel from this side and go through is greater than the chance that a sodium ion will hit from this side and go through the opposite way. Okay. In addition, you have to factor in the fact that the electrical potential difference across this membrane is still negative 40 millivolts, which means that this intracellular compartment still has a lower electrical potential than the extracellular compartment, and it's still lower by 40 millivolts. So sodium has a positive charge. It likes to be where the electrical potential is lower, basically. Okay, so it's going to prefer to be in the intracellular compartment to the extracellular compartment. So that electrical gradient is also driving the movement of sodium in. So what's going to happen, is you're going to move sodium ions into the cell. Now, when you move sodium ions into the cell, sodium ions carry a positive charge, so they are going to raise the electrical potential of the intracellular compartment, and also you're moving them out of the extracellular compartment, so you're going to reduce the electrical potential of the extracellular compartment. So this one is going to go down, this one's going to go up, which means that this overall electrical potential difference is going to go up hugely. It's going to depolarize very rapidly. Okay, and this is known as the upstroke of the action potential. Right, now, after a certain amount of time, however, the voltage-gated sodium channels inactivate. They close, okay, and they stop allowing more sodium in. So you're not going to get any further depolarization of the cell. Now, there is another type of voltage-gated channel that becomes important now, and these are the voltage-gated potassium channels. Okay, so let's draw the voltage-gated potassium channel here in blue. Okay, so here's our voltage-gated potassium channel. Right, so the voltage-gated potassium channels are usually opened, well, they're usually activated to open at the same threshold potential as the voltage-gated sodium channel. So this is a voltage-gated potassium channel. Okay, so usually what happens is that when the membrane was initially depolarized to negative 40 millivolts, that activates the voltage-gated sodium and the voltage-gated potassium channels both to open. The thing is, this one, the voltage-gated sodium channel, opens much quicker. Its kinetics of opening are far faster than the voltage-gated potassium channel. So it opens really rapidly and lets this sodium current into the cell, causing the upstroke of the action potential. It then inactivates. Meanwhile, the voltage-gated potassium channel is just being really slow, so it hasn't yet opened, and it finally gets around to opening just as the voltage-gated sodium channels are finally inactivating. So what happens is, just as this one closes, this one starts opening. Now, it's going to conduct potassium ions. Now, potassium ions, which we'll denote in pink, they are very, very high concentration on the intracellular compartment, okay? And they are a low concentration on the extracellular compartment. So, when this voltage-gated potassium channel opens, the concentration gradient is going to favour the movement of potassium ions out, simply because the potassium ions are more likely to hit from this side and go through that way, rather than one hit from this side and go through that way. In addition, you have to factor in the fact that we are now at a completely depolarized electrical potential difference across this membrane. We usually get up to around plus 40 millivolts, okay, which means that the intracellular compartment's electrical potential is now 40 millivolts greater than the electrical potential of the extracellular compartment. So potassium has a positive charge. It would rather be in the compartment with the lower electrical potential, which is now the extracellular compartment. So both of those things initially drive potassium to move out. Now, when you move potassium out, what's going to happen? Well, potassium has a positive charge, so you're moving positive charge from the intracellular compartment to the extracellular compartment. Okay? So, that means that you're going to raise the electrical potential of the extracellular compartment because you're putting positive charge in there, and you're going to reduce the electrical potential of the intracellular compartment because you're taking it away from there. So this one's going to go down, this one's going to go up. Therefore, relative to the extracellular compartment, the intracellular compartment's electrical potential is going to get lower, i.e. the electrical potential difference from here to here is going to get more negative because you're making this one more positive, this one more, you're making this one smaller. So this one's going down, this one's going up, so that's going to make it more negative. So you go back down like this, okay, and that's how the action potential works until finally these ones close, and then basically you go back to the resting membrane potential because it's all over. Okay, right, so that's the action potential. Now, how do you couple this electrical activity to the release of these neurotransmitter vesicles, which are docked at the moment at the active zone of the axon terminal membrane? Okay, so we have these neurotransmitter vesicles that are all docked here, and we want to cause their release from the axon terminal, basically, and we want to couple their release to the arrival of this electrical activity. Now, the way that you do it is through voltage-gated calcium channels. You convert this electrical signal into a calcium signal. Okay, so the way you do that, should I draw it here? No, I'm going to put it over here, although it will look a little dodgy having the action potential going off over here and then having the voltage-gated calcium channel over here. So here is our voltage-gated calcium channel. Now I'm going to draw the voltage-gated calcium channel in a bit more detail because it's a specific type of voltage-gated calcium channel. Now, so this is a voltage-gated calcium channel. Now, voltage-gated calcium channels consist of lots of subunits. The portion that actually makes up the pore, which is the portion that I've denoted so far, is what's known as the alpha 1 subunit. So this is the alpha 1 subunit here. Okay? Now, there are loads of other subunits also alongside here. So you also have a gamma subunit sitting here. So let me colour the different subunits in different colours. So in turquoise we'll have the alpha 1 subunit. So turquoise is the alpha 1 subunit here. Okay, so this is alpha 1. Okay. Gamma here will be this in purple. Okay. Then we'll have the beta subunit over here. Okay, and we'll colour that in orange. Okay, so this is the beta subunit of the voltage-gated calcium channel. And then finally we'll have this alpha-2 delta subunit here. So this is the alpha-2 delta subunit, alpha-2 delta, made up of both the alpha-2 subunit, this box here, and this delta subunit, which is the portion that spans the membrane. Okay, we'll denote that in red. So alpha-2 delta is in red here. Okay, right. Now, the alpha-1 subunit is the most important. It's the bit that actually allows calcium to move through it. And indeed, you don't actually need any of these other subunits to get a functional calcium channel. They are very important, these accessory subunits, for targeting the channel to the right portions of the membrane. Indeed, this alpha-2 delta subunit is extremely important for making sure that it ends up in the active zone and very close to where the vesicles are docked. Okay, but the alpha-1 subunit fundamentally is the pore, so it's the most important bit. Right, and there are a huge number of different genes encoding for alpha-1 subunits. Now, in the neuron axon terminals like this, a specific alpha-1 subunit is used. In fact, well, not a specific, there are 2 of them that are used over the other 8, because overall there are 10 genes that all code for alpha-1 subunits. And the 2 that we're interested in, because they're the 2 that are used in axon terminals, are the CAV2.1 gene, which gives you an N-type voltage-gated calcium channel. So whenever you hear someone tell you that they have an N-type voltage-gated calcium channel, all that means is that the alpha-1 subunit is encoded by this specific gene, basically, CAV2.1. And actually, I just want to check that, so I'm going to pause the video and just check, because I'm not quite sure